Carlo Séquin has been a professor in the Electrical Engineering and Computer Science Department at UC Berkeley since 1977. His teaching and research have focused on computer-aided modeling and design. For the last 3 decades, his work has been focused on computer graphics, geometric modeling, mathematical visualizations, and on the development of computer-aided design, CAD, which I'm sure he'll describe more of during his talk, tools for circuit designers and mechanical engineers and architects. He has actively participated in the design of 4 buildings on the Berkeley campus, in collaboration with a few sculptors of abstract geometric art. Séquin has found yet another domain where the use of CAD, again, computer-aided design tools, can enhance creative output. And just to let you know, we are going to ask everyone to keep their screens on mute, their mics on mute. If you can, you might want to turn off your video so that all the power of Zoom will go to Carlo tonight. And then if you have any clarifying questions, Carlo has graciously agreed to answer clarifying questions if you want to put those in the chat. Not too many, only if we have some and we want to really interrupt him so that we can understand a little bit more. But most of our questions will be saved for the Q&A at the end of the night. Again, you can enter those questions in as much as you want throughout the presentation, but we're only going to ask them for the most part at the end. And then we can have an open discussion. If anyone wants to raise your hand using the reactions button at the bottom of Zoom, you can raise your hand and we can even call on you. So you can ask your question to Carlo yourself. But again, we're going to wait for the Q&A at the end unless there's an aching question you have of clarification. And with that, Carlo, take it away on the power and beauty of geometry and symmetry.
Thank you, Dee. Hi, everybody. In my talk on the power and beauty of geometry and symmetry, we will leave the world of natural objects, such as plants, animals, planets, or stars. And we will look at the science of man-made artifacts and systems. But first, a little bit more about my background. Let's see. I grew up in Basel, Switzerland, where I attended the Mathematisch-Naturwissenschaftliche Gymnasium. This is a high school with emphasis on math and on science. And during my university years, I heard my mathematical lectures in this 400-year-old institute, where many famous mathematicians have lectured, such as Jacob Bernoulli or Leonhard Euler. And from an early age on, I was fascinated with numbers. During high school, I fell in love with geometry. And then in 11th grade, we had a subject called descriptive geometry, where we constructed the intersection lines between 2 cylinders with compass and rulers. And I thought this was very cool stuff. Ever since, geometry has been in my bloodstream and it has never left me. Around that time, I was also given a book by Hermann Weyl on symmetry. And from then on, I was hooked completely. So what is symmetry? How would you explain it to maybe a 10-year-old or maybe a grandparent who had little mathematical education? Think about it for a minute. What's a good definition of symmetry? I asked this question to a graduate class of computer science students who took a course from me about computer-aided design and modeling, and these were the kind of answers I got. It's like kind of, if you have a mirror. Well, true, there is mirror symmetry. Humans have it, mammals have it to an approximate degree, but there are other symmetries as well. Think about hubcaps. You probably have an intuitive understanding of symmetry and feel that you know it when you see it. Okay, but let's try to capture this notion a little bit more precisely. Here is a mathematically more precise definition. An object is symmetrical if there exists a transformation, such as mirroring or rotation or translation, that maps that object back onto itself. And here are some examples of symmetries in 2 dimensions. First, there's mirroring, and the mirror line may be vertical or horizontal, as shown on the left, or an object may have more than just one mirror axis. Then towards the right, we have rotational symmetries, as you may find in hubcaps or in steering wheels. In the middle, there are the cyclic rotational patterns C sub n. The sub n indicates the fraction of a full 300-degree rotation that you need in order to bring the pattern to coincide with itself. On the far right are some dihedral, that means 2-headed rotational symmetries. Here you can not only rotate the pattern to bring it back onto itself, but you can also mirror it. The sub-indices now indicate that there are 5 or 8 or 20 individual mirror planes, respectively. Now, looking back at the mirror examples on the left, we can see that we can also label them as either D sub 1 or D sub 2, depending on how many mirror lines we have. So if your image or pattern is of finite size, then there are just 2 families of symmetries, the types C sub n and the types D sub n, and that's all there is. End of story. Now, on top of this, we can also translate an object. And this then creates the so-called Frieze symmetries that fall onto themselves when we shift the basic pattern by an integer multiples of the pattern width, which I have indicated by the blue and the yellow double arrows. But strictly speaking, this works only for infinitely long chains. If we have a chain that is only 5 elements long, as shown at the bottom, then there are unmatched elements exposed at the 2 ends if we shift the pattern by 1 unit. Now, there are exactly 7 different types of linear Frieze patterns. They result from different combinations of an axis of glide symmetry, shown in green in rows 2 and row 6, and of horizontal or vertical mirror lines, shown in red, and of rotation centers, shown as blue dots. If you use these blue dots as anchor points and then rotate the whole frieze 180 degrees around it, it also falls back onto itself. There are several different systems for labeling these symmetry types. On the left, there is Conway's notation. On the right, there is the so-called Schoenflies notation, and I will use the Schoenflies notation in my talk today. Now, these 7 Frieze patterns have just used translation in the horizontal direction. If we allow translation of a pattern in 2 separate directions, then we can also generate symmetrical wallpapers. There are 17 different types of wallpapers, resulting from different combinations of mirroring, rotation, and translation operations. For instance, in the upper right corner, there is a pattern that clearly has a 3-fold cyclic rotation in it, whereas the bottom right pattern allows horizontal and vertical mirroring. I hope you can see that it becomes clear here that mathematics and geometry are good languages to capture the notion of symmetry precisely. And this becomes even more important as we look at 3-dimensional objects and their symmetries. Here are examples of 3D objects with a lot of symmetry. In the top row, you see the highly regular Platonic solids, more on them later. Below them, you see the Pentagon building in Washington, D.C. and an octagonal church on the right. All of these elements have many different symmetries. Let's look one simple object more closely. Let's look at the cube. What symmetries can we find in a cube? First, there are 3 mirror planes which are parallel to the cube faces, and also 6 more mirror planes through pairs of opposite edges. Then there are 3 four-fold rotation axes through the centers of the square faces, shown with the yellow lines. Next, there are 4 three-fold axes through pairs of opposite corners. An example is shown in green. And finally, there are 6 two-fold axes through opposite edge midpoints. We can also apply a point reflection through the center of the cube to map the cube onto itself. And we can combine several of these operations to bring a cube into coincidence with itself. So how many different ways are there? Take a guess. To find out, let's mark one face of the cube with a yellow dot and count the ways that this marked face can be mapped back onto the cube. First, the face can be mapped onto any one of the 6 faces. There it can be placed in 4 possible rotations. And we have 2 options. We can either mirror it or not. So overall, there are 6 times 4 times 2 possibilities. So there are 48 ways to map a cube back onto itself. Mathematicians then say that there are 48 elements in the symmetry groups. These are the kind of questions we can ask for all the Platonic solids and for every 3-dimensional object in general. We will come back to enumerate all possible symmetries in 3D, as I've done for 2-dimensional patterns. But first, let's ask, what good is it to know about symmetry? Well, here's some possible answers. For artists and designers, symmetry may enhance the beauty and the appeal of a sculpture or of a design. And for engineers and manufacturers, symmetry may reduce the amount of design work and then maybe the amount of the number of molds you have to do in order to cast the pieces for a big sculpture. And I will show you some examples of that later. Personally, I certainly have made a lot of good use of geometry and symmetry in my work. In many of my assignments during the last 40 years, I have looked for the underlying geometry problems. My first job was at Bell Labs in Murray Hill. I was placed in the group that had just invented charge-coupled devices, and over 3 years, we developed the first all-solid-state TV camera. The success of this then brought me to Berkeley. There, I teamed up with Dave Patterson, and we built the first reduced instruction set computer on a chip, RISC-1. At that time, my students and I worked mostly on layout programs for integrated circuits. Those offered a lot of 2D geometry problems. Then we needed a new home for computer science, and I transitioned from 2D geometry to 3D geometry, building up Soda Hall and a walkthrough program to move around in it before we actually built it. Later, I teamed up with Paul Wright in mechanical engineering on a project called CyberCut, CyberBuild. This started out with the design of optimized tool paths for 3-axis milling machines to make such free-form surfaces as the 3D yin-yang shown in the lower right. Then came along 3D printers and additive manufacturing. And during the last 25 years, I've used these technologies to work with artists and with mathematicians and made all kinds of cool models. The top row shows some mathematical visualization models fabricated on 3D printers. At top left, there's a 3D Hilbert cube with 512 elbows. Top right is a special, highly symmetrical Klein bottle. The bottom row shows 2 larger sculptures that emerged from my collaboration with Brent Collins. All of these involve some intricate geometry and, as you may guess, a lot of symmetry operations. So why is geometry so useful in so many fields? I think it is a power tool for seeing patterns, and discovering patterns is often the basis for true understanding. For some of my sculptures, I find such patterns in inspirational work of more intuitive artists. I then try to identify these patterns and to capture them in the form of a computer program. Then I can produce other sculptures that seem to belong into the same family with the inspirational original. But seeing these patterns really happens in your mind. Now I will try to introduce you to a way of seeing things in your mind that cannot be seen in an ordinary way. Let's start with a simple example. The left figure looks like 6 triangles or like a hexagon with some internal lines. But if you rotate this figure just a little bit, it suddenly starts to look like a 3D cube. This new interpretation and understanding happens in your mind, and the 3D image that you might see is formed by your brains. This is a way of seeing things for which we cannot make physical models. Here is how a high school teacher introduced us to seeing a mathematical object. He did this on a blackboard. First, he drew a very big point that everyone in the class could see. Sorry. Next, he drew a point that was still fairly large, and most students in the class could still see it. Then he drew a somewhat smaller point, and only the front half of the class could see it. Next was a tiny point, and only students in the front 2 rows claimed that they could still see it. At the bottom, he then drew an even smaller mathematical point and asked, who can see this? And those people that could see it, he said, you are the true mathematicians, because I didn't draw anything at the intersection of the 2 yellow arrows, but you inferred that there could be a very small point at that location. That is the power of inferring something in your mind and forming an image of something that you do not have an appropriate physical representation. I will use a similar approach when we later look at 4-dimensional objects. Now let's look at some geometrical object with high symmetry. We will start with some simple geometry in 2 dimensions, since we already know what symmetries to expect. These are the regular polygons. Regular means that all the vertices and edges making up these polygons are indistinguishable from one another. So we can have equilateral triangles, squares, regular 5-gons, 6-gons, and n-gons for all higher numbers. They all have d sub n dihedral symmetry with n mirror lines. There are infinitely many of these regular polygons. Now we go to 3 dimensions. To make a polyhedron regular, all the vertices, edges, and all the faces must be the same. And this means that the surface of these polyhedra are made of the 2D regular polygon tiles that you've seen in the last slide. Here are 5 regular polyhedra known as the Platonic solids. They have been known to mankind for 2 millennia. Now, are there any other totally regular polyhedra? And if not, how would you prove to someone that there are only these 5? In order to construct the surface of some Platonic solids, we must assemble some 2D polygons so that they form a real physical corner. Thus, we need at least 3 faces coming together at each corner. When we then put 3 squares around a shared vertex, then there's still a large open gap. Now, if we forcefully close this gap, then the structure pops out in 3 dimensions, and it forms a true cube corner. And 8 of these corners then form the complete cube. We can also use 3 pentagons as shown at the bottom, and the result will be the dodecahedron. Now we can figure out why there are only 5 Platonic solids. When we use triangles for the surface facets, we have a choice. We can use 3 or 4 or 5 around a point. So 3-sided pyramid or a 4-sided pyramid or a 5-sided pyramid. This leads correspondingly to the tetrahedron, the octahedron, and the icosahedron, which uses 20 triangles. But if we try to form a corner with 6 triangles, we just get a flat, infinitely large tiling. Next, if we use squares, there's only one option. We can put 3 squares around the corner, as I've shown you, and form a cube. 4 squares around the point would just produce maybe a kitchen floor. And we have already seen that with 3 pentagons, we can make a dodecahedron. All larger n-gons are too round and are not able to make 3D corners. They can possibly form some saddles with some convex and some concave edges, but then the edges are no longer all alike, and the solid no longer regular. So this is the proof that there are just 5 Platonic solids. Next, we will try to enumerate all possible symmetries for finite geometrical shapes. Here's a preview of what we're going to find. There are 7 somewhat spherical symmetries based on the Platonic solids, and then there are 7 infinite families of cylindrical symmetries based on the 7 frieze types that we have discussed earlier. Here are the 7 symmetry groups derived from the Platonic solids. The pure, unadorned solids in the top row yield only 3 groups, since the tetrahedron and the octahedron are duals of each other and thus have the same symmetries. In duals, vertices in one correspond to the faces in the other and vice versa. The icosahedron and the dodecahedron on the right are also a dual pair with the same symmetries. All these objects have several mirror planes. But now we can paint some cyclic patterns on all the faces of a Platonic solid. This eliminates all mirror operations, but it still maintains all the rotation operations. So we get 3 more oriented versions of the first 3 symmetry groups in the top row. And finally, there is one last group with some mirroring. We obtain this when we intersect 2 tetrahedra with opposite chirality. Now, the yellow tetrahedron gets reflected into the green one, which has cyclic decorations that spiral in the opposite direction. Now we can analyze these objects as we have done for the cube, and thus find the number of the symmetry elements for all of these 7 symmetry groups. The oriented versions have half the number of elements of their unadorned siblings because there is no mirroring. So these are the 7 symmetries for finite 3D objects. Now we're going to construct the 7 types of prismatic symmetries. We will doing this by winding a finite long segment of one of these frieze strips around a cylinder or around a prism. And in this way, essentially create a 3-dimensional object. Sorry. Okay, illustrating this here, I start with the cyclic freeze pattern Cn, and at the bottom, I show you how we can wind it around a 3-sided prism or around an 8-sided prism or any other number n of units around maybe a cylinder. And we then get an object with either a C sub 3 or a C sub 8 or a C sub n symmetry with one corresponding rotational symmetry axis shown in red. We can do this for any of the 7 freeze types that I've shown you before. And so in total, with those 14 families of symmetry, we can classify any finite object as far as its symmetry is concerned. Some of you may ask, where do all the many shapes go that have no symmetry at all? Do we need to make a special class for those? No, we already have it. It is C1. If you just take one asymmetrical element, as this yellow square with the black dart in it, and wind it around a cylinder, it is a perfectly good representative for the no symmetry class. Okay, what was the next thing we did in 2 dimensions? We added translation. Indeed, we can add translation in 1, 2, or 3 directions. This will then generate some 3D lattices. Guess how many lattices might exist? There are 230 3D lattices. So that's too much. We'll skip them for this particular talk. Instead, since we could handle all finite objects so far, let's talk about the symmetries of 4-dimensional objects. This seems like the next logical question, right? But wait, what is this 4th dimension? Some people think it doesn't really exist, or it's just a philosophical notion. Some people think it is time. But higher geometrical dimensions do exist, and they are quite useful. But you need to use your mathematical thinking to enter that particular domain. I'll try to get you there by this process called extrusion. I start with a point, split it, and stretch it vertically to form a line. Then a second extrusion at right angle to this line makes a square. And a third extrusion perpendicular to both of these directions gives us a cube. In each step, the number of vertices doubles. Next comes the extrusion step that moves us into the 4th dimension and produces a hypercube. This basic extrusion process can continue into arbitrary many dimensions, always moving orthogonal to all the dimensions that we already have. But that last step shown that produces the hypercube is more difficult for us to comprehend. We cannot do this in our own universe, but we can do this with our mathematical seeing. Perhaps we can understand why this is difficult and then overcome our limitations with an analogy to flatland. Assume that there is a plane with 2D flatworms bound to live in this plane. They can move around, but they cannot cross each other or other things. They know about regular polygons, even though they cannot see them the way you can. They can only move around them and measure the length of the sides and measure the angles between them and make sure they're all the same. Then they can see them in their minds. One day, a visitor comes from our 3D world and tries to explain to them what a cube is. She says, just take a square and move it upwards. No, 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 not in a direction, in a diagonal direction, really truly upwards, in a direction that is perpendicular to both edge directions of the square. This is very difficult to do for the flatworms. Same as for us when we try to find the right direction for extrusion to make the hypercube. Perhaps some 4D aliens out there looking down on us and smile at our futile efforts trying to point into the fourth dimension, but it is out there. With our mathematical minds, we can still know a lot about these 4D objects. And we may ask, are there any completely regular polytopes in higher dimensions, like the Platonic solids in 3 dimensions? Polytope is the generalization of polyhedron in higher dimensions. By analogy with our construction of all possible Platonic solids, we know that a regular 4D polytope must have a shell of 3D Platonic solids, and then all corners and edges between these various cells must be the same. But how can we visualize such objects? I have showed you the Platonic solids, but I did not really show you any 3D models. For some of them, I just showed you 2D projections. Did that really bother you? Probably not, because good projections are almost as good as the real thing, because after all, our visual input is also only 2D on our retina. So the 3D viewing is a mental reconstruction in your brain. That is where the real seeing is going on. Now, what is a good projection? Here is an oblique projection of a cube. On the left, I show this projection just as a shadow. Clearly, this is not very informative. It is just a featureless blob. It is much better to project wireframes of these objects. Then we can see them through, we can see through them, and we can also see their backsides and their features on the backside. All figures here are just 2D images, but your brain allows you to see some of them as a cube, as a 3D object. And with a little bit practice, you can also look at 3D projections and then gain an understanding of the 4D object from which they have been derived. But it is important that we take a good projection from 4D to 3D to help our mathematical seeing, just like it is important to take a good projection of the cube. And the one on the right is not as easy to see as a cube as the one in the middle. Here are 2 good projections that we will use. On the left are the oblique projections. Here, the front and the back features of the object are drawn at the same scale, but they are shifted in a diagonal direction. On the right are the perspective projections. Here, the back features appear smaller, and they are typically centered inside the front feature. In addition, we can also use color to give some depth information. Here, the red is the front object, cyan is the extruded back object, and yellow-greens are the transition edges going from front to back. Now, for the 4D objects, I first projected them from 3D space as wireframe objects. Then I projected those wireframes into the screen here as 2D line drawings. Now we're truly going to step up into the 4th dimension, and we're going to try to figure out how many fully regular Platonic solids are there in 4 space. We will apply the same reasoning that we have applied to see that there are exactly 5 Platonic solids in 3D space. Such 4-dimensional objects are typically called 4D polytopes or sometimes polychora. Let's do again what we did for the construction of the Platonic solids. We took a few regular n-gons and that did not fill the 2D space when they were put around the same vertex. And then we forced the gap between them to close, and this popped them up into the third dimension. Now we do this again, one dimension higher. This will make, I will take 3 Platonic solids, say cubes, and fit them around a common edge shown in red on my slide. Here I use the same 2D model again, but now assume that a 3D cube is behind each one of the 3 squares. And once again, we are trying to force this wedge of 3D space. And as we do so, the whole thing pops up in one higher dimension and forms a 4D corner. Okay. Hopefully in your mathematical mind, you can see that this may indeed happen. Now we will count in how many ways we can do this. The crucial value now is the dihedral angle. That is the angle between 2 adjacent faces of a Platonic cells. It tells us how many copies of a particular solid can be fit around a shared edge and how much space is left over. For the tetrahedron, this critical angle is about 70 degrees. For the cube, it is about 90 degrees. And for other angles, they're listed below. So, using tetrahedra, we can fit 3 or 4 or 5 tetrahedra around a common edge without exceeding 360 degrees and still have little room to do some bending into 4-dimensional space. So all 3 options of using 3 or 4 or 5 tetrahedra yield valid regular 4D polytopes. They are respectively called the simplex, the cross polytope, and the 600 cell. With cubes, there is only one valid option. 3 cubes around an edge form a hypercube corner. We can also use 3 octahedra and make a valid corner. This then leads to the 24 cell. Or we can use 3 dodecahedra and then obtain the 120 cell. But the icosahedron is useless. Its interior angle at each edge is more than 120 degrees, so 3 of them do not fit around the common edge. So here we now have seen all the possibilities. There are exactly 6 regular 4-dimensional polytopes. And here are the first 4 of them. The first one is the simplex, or the 5 cell. It's shown in a perspective projection. It is composed out of 5 tetrahedra. 4 of them are squashed and distorted because of the projection from 4D space into 3D space. The second object is a vertex-aligned parallel projection of a hypercube consisting of 8 cubes, which show up here as slanted parallelograms. The third is its dual, the 16-cell or cross polytope. It's made of 16 tetrahedra. And at right, there is the 24-cell composed of 24 octahedra, and this is my favorite. The 2 big ones are coming up in the next slides. Here is number 5, the 120 cell. It has 600 vertices and 1200 edges. Here it is shown in an extreme perspective projection, where the camera was very close to one of the dodecahedral cells, which then ends up as the big one on the outside of this wireframe. And this is number 6. It's a model built by David Richter from drinking straws. This is a parallel projection in which more than half of all the edges are actually hidden by superposition. This is like when you take a parallel projection of a cube and you look perpendicular onto the front face, all you can see then is a square, and most of the other edges are hidden. Okay, here is another view of the 24 cell, which I think is the most beautiful one. This view demonstrates one of the threefold rotational symmetry axes in this object. Actually, this object has 1152 symmetries, but they can only be seen in 4 dimensions. Okay, for the moment, I think this is enough about the power of geometry and symmetry. Now let's talk a little bit about beauty. Let's explore to what degree real artists use or exploit symmetry when they create geometrical sculptures, perhaps to enhance the aesthetics, or perhaps to simplify the design process, and also to reduce the number of molds in the construction of large sculptures. Here are some examples. First, I would like to introduce Hans Schepker. He builds beautiful sculptures from stained glass panels. On top are some of his glass models of the 5 Platonic solids, and then below you can see how he turns these into beautiful Tiffany lamps using stained glass panels. Here is another collection of his beautiful lamps. Some of them are based on the semi-regular Archimedean solids. Others depict stellated polyhedra in which small pyramids have been placed on the faces of the Platonic solids. Hans Schepker also celebrates the 4 simpler, regular 4D polytopes with wireframes and with stained glass panels. And here is a particularly intriguing stellated object. Hans started with a dodecahedron, and then he added 12 5-sided pyramids on all of its faces. This would result in a small stellated dodecahedron. But then Hans cut off the points of all the pyramids and turned them inwards. And that is how he obtains a disappointed small stellated dodecahedron. Cute, disappointed stellated dodecahedron. Next, I would like to present Brent Collins, a sculptor living in Gower, Missouri, with whom I've collaborated for the last 25 years. Here you see him holding our first joint creation, which exhibits D⁻³ symmetry. This shape came out of a program that I created specifically for this purpose, and that program makes a lot of use of symmetry. All it can do is create a chain of stacked saddle elements and then ties them together with a soap film-like surface that is known to mathematicians as Shirk's second minimal surface. With the sliders on the right, I can choose the number and degrees of the saddles and specify how much the whole chain is twisted and bent into an arch or into a closed loop. And here is another geometry coming out of this program. It is a straight stack of 5 monkey saddles with a slight twist. It was carved by the Dingley Stone Carving Art Corporation in China. You can see this sculpture on the UC campus on the 6th floor terrace of the Sutarja Dai building, also known as the Citrus building. Here is a large sculpture that I designed for Brent Collins based on some small hand-carved model that he had made a few years earlier. For something as big as this, one must break it down into smaller parts that can fit into the kiln used for the casting process. And for each segment, one must make a mold. This sculpture has threefold rotational symmetry, so every mold that we have made can then be used 3 times to make a corresponding wax part. which is then used in an investment casting process. Overall, we needed only 6 different molds to make the 18 pieces into which this shape was partitioned. Here is one of the larger molds, and on the right there's a wax replica that was cast in it. These wax replicas are then coated with several layers of plaster slurry. Here the wax is still inside. And then the ceramic shell is sintered in a kiln, and the wax runs out, and it leaves behind a hollow space into which the liquid bronze can be poured. With all the 18 pieces cast, assembly can begin. Here you see a first pair of pieces welded together. Here is a close to final assembly of the whole music of the spheres, with Steve Reinmuth on the right. He runs a bronze foundry in Eugene, Oregon. And here is the last phase of the installation process. And on the right, you can see 2 very happy campers, Steve Reinmuth and Brent Collins. Charles Perry is also one of my heroes. His work inspires me to create intriguing geometrical sculptures. On the right is one of his rather well-known sculptures called Continuum. It stands in front of the Aerospace Museum in Washington, D.C., and exhibits D sub 3D symmetry, threefold rotational symmetry. Here in the Bay Area, you can enjoy one of his creations in the Hyatt Regency Hotel in San Francisco. Overall, it has dodecahedral symmetry with 12 gigantic pentagonal windows. Here is a simpler sculpture. He made 2 versions of the same basic geometry. The one on the left is called tetra, because the metal bands follow the 6 edges of a tetrahedron. But since 4 of the 6 ribbons are twisted, the 24-fold symmetry of the tetrahedron is lost, and the sculpture now has only 8-fold D sub 2D symmetry. The second version of the sculpture, Charlie actually named for its symmetry group, D2D. I guess these examples should convince you that some artists do indeed make conscious use of symmetry and mathematics. But now, as a counterexample, I want to give you a glimpse of another artist who is mostly avoiding symmetry. Eva Hild lives in Sweden and creates beautiful flowing ceramic surfaces with intricate connectivity. Eva often builds several surfaces in parallel over a period of several weeks without a concrete plan for a final result. Those forms then just grow organically around some envisioned inner space. Eva reports that often she is surprised herself by what the final shape turns out to be. I just want to leave you with this thought that you can also have a whole lot of beauty even without any symmetry at all. Thank you for your attention, and are there any questions?
That was a wonderful, thank you so much, Carlo. So I do have some questions. Oh, well, let me ask one of the questions that came through, and then maybe we'll switch. I know, let me see so I can pull up everyone's hands. Were those folks that you just mentioned, Carlo, the different artists that you mentioned, are they trained mathematicians as well, or do they happen to be good at math and artists? Or I know you have both things going for you, right? You're an artist and a mathematician. So what about those folks?
It varies widely. So on one extreme is Brent Collins. And he knows sort of nothing, or did know nothing about math at all before we ever got in contact. He just intuitively saw soap films in nature and then carved surfaces that have this minimal performance of a typical soap film spanned by some irregular structures. He liked intuitively symmetrical structures, so he built these totem pole-like things with stacked saddles, but without any twist or without any extra elaboration. And then there was a professor from Illinois who pointed out to him that actually some of the surfaces that he had intuitively created were surfaces known to mathematicians. In particular, there is this Shirk's second minimal surface, which forms these kind of towers of saddles. And he explains that to Brent. And then together they wrote an article in the journal Leonardo. And I saw the article in Leonardo, and it's the first time I heard about Brent Collins. And so I tried to figure out who he is. Eventually I found out he lives, out in the boondocks, north of Kansas City in Missouri. And so I called him up, and he was so glad to be able to talk to somebody about that, because in his neighborhood, nobody has any clue what he is doing and what it all means. And because he knew about minimal surfaces, he had heard about the Shirk's second minimal surface, we had something to talk about. The first question we asked is, what would happen if we changed the number of saddles in a ring and make it an odd number? And we figured out it would then become something like a Mobius band. And that got us really excited, and we tried to figure out what would happen. So over the next few months and years, I think he got to learn more and more about the mathematics behind his sculptures as I explored his designs and tried to understand them from a mathematical point of view and create a program that I could really use in order to create more of these kind of objects. Now, I think Hans Schepker, on the other hand, he is definitely an artist, but he knows his polytopes very well. He has no problem understanding the fourth dimension. And so all the stained glass objects he did, he fully manages the geometry and the mathematics sort of behind them. Now, in the middle is Charlie Perry. He knew about Mobius bands. He calls them Mebius bands. And we had interesting discussions about it. And he often twisted ribbons. And but he didn't always use the nomenclature quite right. And when you see the sculpture that he named D sub 2D, he actually only put the 2 in the sub and not the D. That's not quite correct. But he is the artist. He can name his sculptures whatever he wants. And then finally, there's of course Eva Hild. No mathematics whatsoever. She doesn't even want to know about symmetry. She grows these things with an intuitive, organic sense that there's beauty and there's a shape that she wants to capture. So it varies all over the place.
Interesting. Yeah, I just want to mention, because I didn't mention yet, that actually you have been involved in all of our science and all of our art shows, science and art shows, since 2012. I wanted to say that you are an artist as well as a mathematician, and you are very prolific, clearly. And thank you. Carlo is near and dear to our heart at Science at Cal. I didn't mention, because he is also one of our council members, our advisory council members. So I didn't mention that. I meant to mention that to you, Carlo. Thank you so much for all the years of your service. And now I'm going to hand things over to Thomas Klein. If you want to unmute yourself and ask a question, Thomas, you're more than welcome.
I must say, Carl, I realize how difficult it is for mathematicians to communicate to non-mathematicians. And I think you did a marvelous job. It is really tough. I'm intrigued by this question of the beauty of symmetry versus the beauty of asymmetry. I do find Eva Hill's asymmetric artwork is a little bit cheating, because to the non-mathematician looking at that right away, I couldn't immediately identify that as asymmetric versus your symmetric artwork. But what struck me years ago when I first went to Barcelona was seeing the architecture of Gaudi. And I don't know how familiar you are with Gaudi, but everything he did is asymmetric. But it's asymmetric in a way that you can recognize the asymmetry, but it's still beautiful. And I guess the question is there a question in this? The question is the beauty of symmetry versus the beauty of asymmetry. And I find it difficult, maybe everything's beautiful, but what makes, there's certainly unbeautiful asymmetric things. I don't know if there are many unbeautiful symmetric things. Most of them tend to keep their beauty. But I wonder what you think about the beauty of asymmetry versus symmetry, why it should matter to humans.
Well, that's a deep question. Of course, we don't even know what beauty is, and ideas go very much apart of what beauty is. And so I'm sometimes even reluctant to be called an artist, because I'm certainly not fitting in with the art scene in New York, and then they would laugh me out because, you know, I'm not bleeding hard enough. I don't address, you know, the problems of society in my work. I'm not doing the first thing ever, you know, putting some dog poop on the road and photographing it from an angle and call it, you know, thing. I'm happy to say I'm a designer. And I think a designer, you know, has a theme, he has a goal, and then the designer works a particular theme again and again and again until it gets it sort of perfect, right? And so design and engineering are much closer together than really art and engineering. But now about, let's see if I can find something here. Yep. Okay. You talk about Salvador Dali. You know what this is? It's corpus hypercubus. Just how we can take sort of a, you know, 6 squares in paper, make a cube, and then unfold it to make a net. We can do that in 3 dimensions. We can take the 8 cubes of a hypercube and kind of unfold them into this particular sort of 3-dimensional cross. And clearly that particular cross is very, very highly symmetrical. So Salvador Dali really understood those things, and he played very judiciously when to use symmetry and then when to deliberately break symmetry. And often you get a special kick out of something by starting out with a symmetry and then just kind of put one twist in it. I think the Japanese often feel that, you know, perfection and perfect symmetry is not a good thing. It offends the god. And they want to put something in there just to break that symmetry. So there are all kinds of philosophies when symmetry is a good thing and when you really don't want to have complete symmetry. That's the best answer I can give.
Thank you so much, Carlo. Rosalind, do you have a question from the chat that you'd like to ask?
I do. Carlo, we have a question about how has 3D printing transformed your understanding of symmetry, if at all, and how has it transformed your ability to sculpt?
I think it hasn't enhanced my understanding of symmetry, because that was going all the way back to this book by Weil, and then following up and teaching, you know, many years. I teach graduate courses in computer-aided design, and I taught symmetry and all that long before we had 3D printers. And so my personal understanding of symmetry has not increased. But what really has happened is I can now make these complicated objects. I mean, without 3D printers, you can only make 2D objects, and then you can rotate them at best, and you see what you're seeing right now. But actually having this object and touching it, and then having a whole lot of other objects that you can actually look at and rotate and maybe even mark up to have the symmetry, it certainly has very much increased my ability to convey those ideas to my students and to explain things and to make all kind of incredible, wonderful models, some of which I then, again, with collaboration with some artists, we decided, oh, they're worthy enough to be scaled up, and we make a real sculpture out of it. So for me, the 3D printers are just a fantastic toy to get all of these models and have them in a way where people can really enjoy them. I think it was Helaman Ferguson, a famous mathematician who is also a splendid artist, maybe the number one person in the universe with the biggest product of mathematical knowledge and artistic knowledge. Helaman Ferguson really says that you want to make sculptures to be touched. And in his book, basically there's a photograph where he hugs one of his sculptures to drive this point home. It says, to make a sculpture that you're not allowed to touch, that's kind of really wasted. And I sympathize with that.
Going back in time, I mean, now we have our 3D printers, but this is a great question. How did MC Escher create his art without computers to generate the translation? And did you ever meet him to discuss these topics?
He is absolutely awesome. For 22 years, I've been involved with the Bridges Conference. That's an art and mathematics conference that started in 1998, where we try to show the connection between mathematics and many of the other cultural venues that we have, including, of course, painting and sculpture, but also macrame and maybe origami and design and dance and music and even poetry. All of these things have mathematical structures in them. And in our conference, we try to point this out and show the mutual influence between mathematics and these other domains. So this outreach and showing that mathematics is more than just rote learning of multiplication tables, as we do sometimes in our primary school, is a very big interest of mine. And this conference is ideally suited for that. And we have a lot of artists coming it. We have a lot of teachers, even high school teachers coming to it. And the interaction between all these various people is just wonderful.
Great, thank you for that. Rosalind, do you have another question from the chat?
I do. So on a similar note, someone mentioned symmetry is appealing to all, and so is the golden ratio. Is there any connection between those two? In addition, symmetry is also really pleasing in music. And is there any theoretical relationship with symmetry or geometry in those groups?
Well, let's start with Johann Sebastian Bach. Of course, he was a mathematician as much as he was a musician. And so he explored probably symmetry more than everybody else in the music world. He took the score and ran it backwards, and he took the score and ran it upside down and ran it upside down and backwards, and did all possible mathematical operations that you can only imagine on his score, and then, looked how it sounded. And typically, if you have a nice tune to start with, it's still actually good, even in applying all of these variations. Let's see, what was the other part of the question?
About the golden ratio, if there's
the golden ratio. That's a that's a strange thing, because frankly, the golden ratio is highly overrated and often leads to enormous nonsense being said about it and published about it. It is just a ratio. It's an interesting ratio, and it's clear that the Greeks in some of their temples have consciously used the golden ratio. But then some people, they try to find golden ratios everywhere. They look at the head of the Mona Lisa and they try to make a rectangle, and of course it fits. Because, who says whether you should include the ears or not include the ears and how much of the hair you include, right? So you can certainly fit a golden ratioed rectangle around the head of the Mona Lisa. And they take any kind of structures they can find or any kind of paintings, and they put rectangles in there and always, find the golden ratio and then have deep philosophical discussions about the meaning of it. It got so bad that at Bridges, pretty much, if a paper has golden ratio in its title, we reject it pretty much without even studying it. So you can see golden ratio, it's just one of many possible ratios. As a matter of fact, when you ask most people what makes a nice rectangle, is it a good rectangle or would it be more beautiful? The peak is not at the golden ratio. It's really a different ratio that people find is the most pleasing rectangle, not the golden ratio. So anyhow, sorry about dumping on the golden ratio that much.
I love your strong feelings about the golden ratio, Carlo. Thank you. It shows some passion there. Okay, I'm going to ask you a series of questions about your favorite. So Name your favorite shape to say.
Favorite what?
Shape to say. They all have such crazy names. Do you have a shape that you love the name of?
Still didn't get what my favorite what?
Shape is to say.
Shape.
Yeah, the shape, a shape.
Oh, well.
The word.
Yeah, I mean, as I mentioned, among the four-dimensional Platonic solids, I love the 1152 symmetries of the 24 cell, which is made from 24 octahedron, because it's not so busy like the two big ones that you cannot understand what's going on. And it is, not quite as simple as the lower three. So for me, this is clearly the jewel among those. And it turns out, before I even knew that this object had that many symmetries, I moved in Berkeley at Grizzly Peak Boulevard 1152. Now, how much of a hint of fate is that, that I'm living at the address 1152, that and my favorite object here has 1152 symmetries. So there's clearly some cosmic coincidence there, right?
Yeah, definitely. What's your favorite sculpture?
Oh boy, that's like, asking some mother to ask, what's your favorite child, I mean, I'm going to pass on that one. Sorry.
Okay. How about, and I think this question is more like who's your favorite child? Do you have a favorite sculpture that you worked on? Maybe because of collaborators or that you personally worked on? You can pass on that too if you don't want to.
No. I think it's the evolving trefoil. All right, let me kind of skip that here. Let's see if I can get out. I think I can find a picture of it. Let's see. All the trefoil. So look at the lower right. Okay. Lower right is essentially a very long stack of these kind of monkey saddles. Okay. It has actually 24 of those saddles stacked on top of one another. And then that whole chain essentially is wound around and formed into a trefoil. So clearly the basic stacked saddles came out of the inspiration I got from Brent Collins, who was the first one to kind of, carve such stacked saddles, essentially directly mimicking the second minimal surface by Mr. Shirk. And this is also in Missouri Western State University in their science building. And they wanted an outdoor sculpture, which I've shown you, that was the Music of the Spheres. And they also wanted an indoor sculpture. And I essentially proposed that to Brent. So basically, other than the basic idea, which is his motive, the whole design and the arrangement, that's something I did mostly of myself. So in the collaboration, this would be maybe 90% on my side and then 10% on Brent's side. And so given this evolving trefoil, which is really an evolving set of ideas from a simple stack of saddles and then bringing in arches that curve and then essentially making loops out of them and then making loops that actually forms a knot. Really, there's an evolution of complexity and an evolution of thought. And I like that. And so particularly in Missouri, they need to hear the word evolution every now and then so they don't forget. And so we call them the evolving trefoil. And I certainly refer to evolution when we gave the speech at the opening of that particular sculpture.
Good for you. You're on the All of the same, we're on the same team here. That's great.
Science at Cal, yes.
Yes. Rosalind, do you have another question from the audience on chat?
Speaking of evolution, Carlo, we had a question from the audience. Why did symmetry evolve to be so appealing to the human brain? Is there some sort of value to that?
Well, I think among humans and mammals, we have this bilateral mirror symmetry. And, of course, they're not totally symmetrical. You can do that. You can see that if you have cut your face in Photoshop and then paste two of them together. But they're reasonably symmetrical. As a matter of fact, somebody is really grossly asymmetrical, that does not look good, So when you go out and look for a date, you probably don't pick up on people that are grossly asymmetrical, because very often such asymmetry may be a sign of a disease or a defect or something like that. So I think our evolutionary history has favored somewhat the symmetry because it's a sign of health, and we can refer to it and we think it's the natural thing. And I think then later on, it kind of progress to having other kind of symmetry. At some point, the Neanderthal people started to carve maybe star patterns into bones, or essentially discovering rotational symmetry with 3, 4, or 4-fold, or even 5-fold symmetry and things like that. So I think it's of an evolutionary process as humankind started to think about our own symmetry, and then maybe discovering that there are other symmetries, like starfish with nice 5-fold symmetry. And so very often in flowers, you often find 4, 5, 8 petals or something making nice symmetry. So symmetry exists in nature, and they're typically associated with beautiful things, creatures or plants. And I think that developed that notion, and then humankind latched onto it and developed a more stringent definition of symmetry and a more deeper understanding thereof.
So we have a series of questions about basically being the brain and being able to visualize these different dimensions. And I loved your flatworm analogy, and then the aliens, Martians looking down on us and judging us for only seeing 3D. That was great. So questions like, are certain people better at seeing in multiple dimensions? Can you visualize in a fifth dimension? For one of our viewers, they say it's very difficult for them to imagine that, which I'm sure is common for most people, right? So are some people more able to do that? I know you said it takes practice, but have you gotten good at it?
So I must admit, I cannot really see 4-dimensional objects. Mm-hmm. I typically reason by analogy. I see kind of what happens when we go from 2D to 3D, and then I take the same step and say, well, if you go from 3D to 4D, there's something equivalent. And the best example, of course, is the mainstay of this talk, where we developed the 5 Platonic solids from the 2D regular polygons. And then by doing exactly the same process, we took the Platonic solids as kind of a thick crust, and by the same kind of symmetrical arrangement, making a shell that now defines a 4-dimensional regular object. So I'm not sure at what point I will call something seeing or not seeing. I mean, the hypercube pictures that you see, they make perfect sense to me. Of course, they're not totally symmetrical, showing all the details, but they show a lot of good stuff, all the connectivity and how many edges come together at the vertex and the like. So I think they're good depiction, even though it's not really seeing the 4-dimensional object, it's seeing a very good projection into 3 dimensions. I have not encountered anybody who claims that they can really see the 4-dimensional object in its full glory with all its symmetries per se. So most of the people I talk to, they argue in the same way that I do, by analogy and by the equivalence from 2D to 3D. So I don't know whether there's any brains out there that have developed this higher intuition that they can really claim that they are seeing 4D objects.
Great, thank you. I think Rosalind has one more question to you about the program that you created.
Yes, Carlo, we were wondering, how do you manipulate the program that you made to get different designs, and what are the kind of different variables that you can use?
There are multiple different programs. So the first one is the one that I showed you a brief glimpse of. Let me see if I can catch that again. Let's see. Okay. So this is the program which I did, well, I guess 25 years ago, when I started to interact with Brent Collins, which I call Sculpture Generator #1. And you can clearly see the kind of stacked set of saddles here, which forms this pipe. I think at the moment, if I look at my numbers here, maybe I have about 8 stacked saddles. But then in addition, it has sort of been given a twist. That's a very special purpose program in which I try to capture some of the basic geometries that Brent Collins has developed with his stacked totem poles. And with something that, as I showed you in another picture, our first joint sculpture was 6 of those saddles in a nice symmetrical rings, which he calls the hyperbolic hexagon #2. So I captured those kind of shapes, and then I just varied the parameters, the number of saddles, and whether they're single saddles or monkey saddles or 4-fold saddles or whatever, and how much it's twisted and all that. Now, for many of the other things, like in particular to capture something like that, that's an entirely different geometry. So I need different programs. Over about 10 or 15 years, from say about 1990 to about 2004, my graduate students and I developed the Berkeley slide environment. And this is essentially a procedural graphics language that allows to specify in a somewhat procedural manner the geometry of many objects that have a lot of symmetry. So here, because of the high symmetry, I only need to design 1/6 of that object, and then I make 3 copies around and I mirror it, to get the other half. And so that makes it much simpler. Or here, the symmetry is even higher. Here I only need to do 1/20th of that thing and then replicate it. And that particular language makes it really easy to specify a primitive cell and then say exactly whether you want to apply dodecahedral symmetry or icosahedral symmetry or whatever to make these geometries. And more recently, I've started with a new program development where every year I have a few undergraduate students working on it. And we call that GNOME for the non-orientable manifold editor. A non-orientable manifold is something like a Mobius band or a Klein bottle that has no real front side or back side or inside and outside. You can seamlessly go from one place all the way around and end up on the other side of the face without ever penetrating the face or stepping around one of the sharp edges. In Slide, we have some trouble with those kind of objects because at that time, that was not something I really needed to do. And so we started a new development replicating many of the things we have in Berkeley Slide in this GNOME environment. And so now we make sure that we can do Klein bottles and Mobius bands and all kind of other single-sided surfaces. And that's pretty much the domain in which I have created most of my sculptures. If you want to go and find a commercial program that can do this, Rhinoceros with the various front end like grasshoppers or so would be something I could recommend. Many of my colleagues and friends that participate in the Bridges Art Math Conference, they're using that particular program. And then there is the public open SCAD. Open SCAD has many of the capabilities that we also have in Slide. It can start out with a procedural definition and then enhance it somewhat by graphically modifying it. So there is a spectrum of things. The main thing is it's not something that's only just interactive on the screen. I mean, there are many good programs that interactively can do all kinds of the screen, but in those programs, it's very difficult to keep control of exact symmetry. You can make lumpy potatoes, you can make, fuzzy teddy bears or whatever, but to make a structure like shown here on the left of my slide is almost impossible by just purely manipulating vertices and features in an interactive manner on the screen. You need to specify those geometries with some procedural program.
Okay, so we have only 2 more questions, so we'll wrap up soon. Have you worked with any architect, Carlo? I know you talked about all the sculptures.
As a matter of fact, yes, I have. I collaborated with Yehuda Kalley in the School of Architecture here on the Berkeley campus. This was after we had built Soda Hall. I was very heavily involved with Soda Hall. I worked side by side with the architects, making sure that we would not only get a beautiful building, that's their job, but a functional building. And in order to make sure that we get that, we created an interactive walkthrough program in which we could walk through the finished Soda Hall building, before we actually built it. And people often say that it was because of that program that Soda Hall turned out to have essentially 100% satisfaction rate on day 1 when people moved in. Now, it's only part of the story, because how did we build this particular model? Well, we worked with the architect from his blueprints and from all the floor maps that he made. And we probably spent between 50 and 100 hours to extrude the plans of the architect into a 3D model. Now, when you spend 50 to 100 hours to look at what the architect proposes, you ask all the right questions. You say, why is this door opening to the left? Wouldn't it be better opening to the right? Couldn't we move the door 1 foot away from the wall? Because then we could put the bookshelf behind the door, or we could put the bicycle rack behind the door. If you have a conference, where would the conference be? Where are the breakout sessions? Where would we serve coffee? Where do we hand out, the badges and the like? And so it was really the process of making that model with constant feedback to the architects on questioning things and making small changes that we had essentially the perfect plan before we ever turned on the program. Once we turned on the program and we started moving through the program, there were no surprises. Oh yeah, that's exactly how we expected it. Yeah, of course, and the like. So it was doing the homework properly in preparing that 3D model that made this a successful building. There were other buildings on campus where the architects presented the plans, the faculty looked at it for 10 minutes. And then 2 years later, when they moved into the building, they complained, why is my office behind a fume hood? I always have to pass a fume hood. Well, it was in the plans. They could have looked at it. They could have caught it had they spent more than, maybe 1 hour looking at the plans. So we had that benefit that trying to make that model in Soda Hall. We spent a lot of time looking at that. And I guess that then got me involved with also doing the Citrus building and doing the building next door with all the 3D printers, and on a couple of other buildings, I acted as a consultant. After that, I teamed up with Yehuda Kalley, and we taught a joint graduate course with some of my graduate students doing CAD tools and some of his students doing the building. We took the exact same plans, the program essentially for Soda Hall, 20 faculty and so many students and the like. And we picked a new location, which was just west of Evans Hall. And the task was, let's build another building there, okay? And then my students had to watch the architectural students to see how do they go about, what are they doing when they do the process? And then after watching them for a couple of weeks, our students had to create CAD programs that would help the architects to make that process more efficient. And then we forced the architects to use those tools and essentially give feedback how useful those tools really were. And so it was an interesting collaboration, bringing architecture and computer-aided design together to increase the way buildings could be designed.
Fascinating. I know once you start getting good at things, then you're going to be asked to do more and more and more projects, right? When they know you've done a great job.
That's right.
So last question. Are there any examples in nature of animals or plants that you know of that leverage symmetry of colors or sounds for either camouflage or hunting, those sorts of things biologically?
Well, there's certainly a lot of animals that use camouflage, but typically because nature in general is not very symmetrical, they're more like, our military suits, that kind of, are random patterns of brown and reddish and green and so on and the like. And of course, the octopus can, change their colors depending on the kind of sand or whatever they're lying on. But all of this really has no symmetry whatsoever. Now, if the turkey goes and blows up his big wheel, right? It's a very nice symmetrical design to impress the females. And again, if it's nice and symmetrical, they probably think that's cool. If it were to look like that, they say, no, not my mate. So I think for maybe sexual attraction, many animals use symmetry because that seems to be attracting, the other sex. Other than that, I cannot think of an immediate example where they would use symmetry to camouflage.
Yeah. Well, I said last question, but actually I'm going to let everyone know, because we talked about this earlier, that if they want to learn more, they can go to your website, and maybe we'll send this out when we send out the email of the video, and they can take a look at your slides and other presentations that you've given. And how this relates to my last question is, do you have any recommendations for books that you might suggest if people want to learn more about this? I know you showed me a book earlier. I'm wondering if that's the book you'll pull out.
Well, Hermann Weyl, Symmetry, is a good book, and it excited me when I got that, in 11th or 12th grade. I mean, I got hooked, and there are pictures in there of viruses that don't have dodecahedral symmetry and all kind of other things. So certainly it's a good way if you just want to look at symmetry. Let's see, do I have this book here? I cannot see it immediately. Let's see, symmetry. There is a really good book called The Symmetry of Things by Horton Conway. And he takes a different approach of describing symmetry, but it's very complete, and it really goes through the free symmetries, and it goes through the wallpaper symmetries and all of that. That would be a very solid textbook for a graduate course on symmetry. So if you really want to go there, that would be good.
Who's the author again? Who's the author?
Conway, C-O-N-W-A-Y.
Okay, I found it on Amazon. I'm sharing it with everyone. There you go.
Conway notation that I briefly mentioned that on the left slides. But okay, if you Google Séquin and Berkeley, you'll definitely find my homepage very, very quickly. Now on the homepage, you can see more sculptures. You can see the talks I've given recently. You can see papers I've given. It's all documented. But you can also go to some of the courses I've taught. One is a freshman seminar about symmetry and topology. And you can go and see essentially lecture by lecture what we're doing in there. Another would be my course 248, which is sort of a graduate computer-aided design course. In both of those courses, if you go essentially to the homepage of the course, you actually find a listing of typically 3 or 4 books that refer to that particular topic. And there you may find other topics like the knot book that describes geometrical knots, or orderly tangles, a book that talks about interlinking links that make highly symmetrical objects. So in both of these courses, up front on the homepage, look essentially for recommended books.
Perfect. You have lots of recommendations for us, lots of information. It has been a pleasure. Thank you for waiting an entire year to share this with us. I know you were scheduled last March, and And we had to
It
postpone.
only got better in that 1 year.
Well, again, thank you for being part of the Science at Cal community. Thank you for always saying yes to being a part of our lectures and all of our programs, and for continuously adding your advice and support during within our advisory council, in your advisory council role. So thank you again. Thank you everyone for joining us all the way from Australia. That's amazing.
And as we say, go Bears.
Oh, go Bears, everyone. Thank you again for being here, and join us. We have a talk in 2 weeks, so join us again then. So thank you, everyone. We'll be in touch.
Sure. Okay. Bye, everybody. Thanks for your attention.